Hello. This is the third lecture on Chapter 5 about binomial distribution. So we are going to finish this chapter today. I expect this lecture will be rather shorter than usual. So let me review what we have done last time. So the main theme of what I did in the last lecture is to derive this answer, to give you the solution to this seemingly simple question. But actually, this question is not that simple. So remember, there were 10 reservations, and probability of each cancellation is given, and cancellations are independent across the reservations. In this case, we would like to know the distribution for the number of cancellations, right? That is the binomial distribution. And to get to the final answer, we had to take these steps. And I want you to observe the patterns and how they operate. And then in the end, we can understand the complicated formula better. So then first, you need to understand the independence, which is just so actually mechanically simple. It's just I would like to break down the intersection into multiplication. And then when you consider two reservations, then what I want you to see here is that there are four possible outcomes. Here you have to understand that there are two different outcomes that satisfy one cancellation. That imply y equals 1. So y equals 1 is not a single outcome. It consists of potentially more than one outcomes like this. Even in the simplest possible case, you have to think about two cases because one reservation is canceled, but you don't know what is canceled, what is the canceled one. And also, another thing you have to realize here is that you need to consider this probability. So when you calculate the probability that A is canceled but B is not, it's not simply 10%, even if the probability of cancellation is 10%, but you have to take this into account. So B is not canceled, so you have to multiply 0.9, the probability of non-cancellation. So that's one thing I want you to realize. And another thing is that there can be more than one outcomes that correspond to this event. And then from there, we are going to generalize. We will generalize to the three reservations case, which is straightforward. The only difference is it's more complicated. It just has more possible outcomes. So you should be more careful in counting the number of outcomes that belong to this event. There are three different outcomes. However, what we can see here is that even though there are three outcomes, we do not need to calculate three different probabilities. Those three outcomes have exactly the same probability. Therefore, we can split. What we learn here is we can divide these two parts. You can separate the probability into two parts. One is the number of outcomes that correspond to this event. And the second part is the probability of a single outcome. It's about single outcome. So we can consider these two parts separately. The second part is easier because it is easier to understand. The idea is you multiply probability of success as many times as the number of successes, right? And multiply the probability of failure as many times as the number of failures. So when you repeat n experiments, y is the number of success, then n minus y is the number of failure. So you have to multiply their corresponding probabilities. So p is the probability of success, 1 minus p is the probability of failure. So multiply them. So this part is rather straightforward. The annoying part is counting the number of possible outcomes. When you have 4 reservations, we find that there are 6 different outcomes, 6 different combinations of 2 reservations out of total 4. So then where did this number come from? How do we get 6? The answer is this complicated, even more complicated rule. So it's a combination rule. So it's not easy to do this, but just there is a pattern. So this rule is an abstract way, as a mathematical way to generalize how we can calculate the numbers, right? And I gave you some examples, simple examples, and simple tips. Multiply the same number of numbers on the denominator and the numerator, and the starting numbers are different. Starting numbers are given by these two. So denominator goes down to 1, but numerator ends at a certain point when the same number of numbers are multiplied. So usually there are some cancellations, so canceled out. So the numbers would be easy in some cases. And then combining those two parts, we get a general formula. This is the general formula for the binomial distribution probability. So when you repeat a binary experiment for n number of times, and each experiment has a probability of success p, then the probability that the number of success equals lowercase y is given by this thing. So we need several assumptions, and then it also takes a while to get to the final probability. But in the nutshell, we need 2 parts. We have only 2 parts, and this part is just a simple formula, and this part, and it can be understood intuitively. So this is what we derived in the previous lecture. And so as a result, the answer is 19.37%, which is very counterintuitive. So the answer is obtained this way. And I told you there are 2 common mistakes in doing this. One is, the first one is to ignoring the probability of failures. Usually when I say 2 reservations are cancelled, you may not think of the other side. Its flip side is that 8 reservations are not cancelled. So you have to consider this probability too. And second, it's not a single outcome. There are multiple outcomes, so you have to consider those different scenarios, different combinations. So if you understand those two, it's more clear why it's more complicated than it looks. Okay, then back to the binomial distribution. Derivation was over. So we have a binomial distribution. We set 4 assumptions. We had 4 assumptions to define a binomial random variable, and a binomial random variable had 2 parameters: n, number of experiments, and p, probability of success. And given those assumptions and the parameters, you know that y, which is the number of success, can take n plus 1 different values because it can take at minimum 0. So if there is no success, y will be 0. And if everything is success, then y will be n, which is the maximum. This is the minimum. So from 0 to n, there are n plus 1 integers. So y can take y, the random variable y takes on n plus 1 values. So therefore, there are n plus 1 different probabilities. We can think about n plus 1 probabilities, and if you know those n plus 1 probabilities, then you know everything about the binomial distribution, right? So there are n plus 1 possible outcomes. So you need to know n plus 1 probabilities to fully understand the binomial distribution. But what we just derived, the formula for the probability, is given by this. So by changing y, lowercase y here, the lowercase y can be 0 or can be n or any number in between them. So the lowercase y changes to n plus 1 different values, and when it changes, it gives different probabilities. They are the distribution, right? So other than this, so lowercase y it's what you calculate here, the point you are calculating at. And then other than lowercase y, n and p are the only parameters you need to calculate this probability. That means you only need two numbers. If you know parameter n and parameter y, then calculating n plus 1 different probabilities can be, those probabilities can be calculated according to this formula, right? So that's what I meant by the two parameters fully summarized, do not lose any information, and fully contain all the information about the binomial distribution. So if you know the values of these two numbers, then you can calculate n plus 1 probabilities. So you know everything about the binomial distribution. So that's the power of model. So as I said at the beginning of this chapter, under those, if a random variable satisfies those assumptions, the given assumptions, then you can summarize the distribution pretty easily by two numbers. And then, like if you calculate, the shape of the distribution can be depicted like on Excel. I did it on Excel. So think about 20, n equals 20. So it's like you are throwing a coin 20 times. Then the distribution would be like this. On average, you will get heads about 10 times. But sometimes you are going to see more than 10 or less than 10. It depends. It depends on your luck. And there are, of course, the probabilities will be extremely low for large numbers and smaller numbers. And distribution is like this. So this is calculated based on the formula we obtained. And if you change the probability of heads, like 90% or 10%, the distribution changes. When you have 90% of heads, right? When you throw a coin, say the probability of head is 90%, then on average, the number of heads you see from 20 coins would be near like 18. 90% of 20 is 18, so probability will be high here. And it will be extremely unlikely to see like 10 or fewer heads because it's so likely to be head. And if you change the probability to 10%, exactly the opposite, right? So it's more likely to see 1 or 2 head out of 20 and unlikely to see more than 10. So these two numbers give 21 different probabilities here because n is 20. There are 21 possible values and two parameters. By changing those two parameters, you can change the shape of the distribution. The shape of the distribution can change depending on those parameters. Okay, right. So in the next video, I'm going to show you how to calculate the probability on Excel because you may want to use Excel on your homework, like especially when you calculate the combination rule. Combination rule, I told you the formula, but it's not easy to do it by yourself. So I'm going to demonstrate a simple Excel function to implement that. Okay, see you later. Bye.